Anyway, it was a bit over 4 years ago when Nathaniel reached out about a potential PhD at Northeastern. And personally, I had no ambitions of taking on, hyperspectral imaging for robotics as a new research direction. And I really tried a few times to deviate him from his vision and then his path. It didn't work, as you can tell. So today we are here for Nathaniel's dissertation defense. A PhD is a long journey. I always say this to my students. You develop lifelong conflicts of interest with your advisors. In this case, Chris Dorsey and myself. And every PhD is supposed to have its own ups and downs. Every PhD is supposed to have its own, arguments, disagreements, and agreements. But then at the end, we reach a point, and it's time for the student to graduate and move on. So today's activity, today's presentation is like the capstone of what Nathaniel has been working on for the past 4 years. He's going to tell you what he did. And then in terms of the logistics, there's the presentation is public, so Nathaniel will present. Unless you have a dying clarification questions, we'll keep the questions all the way to the end once he's done with his presentation. And then we will open up to the public, right? So everybody can ask questions. Then there will be a session where we will ask you to step outside. You can have all the leftover goodies and the coffee with you. Then the committee will remain with Nathaniel to ask him questions. And then the committee will have another quick session where we talk about what happened and what to do next. Does this make sense? Any questions? Okay, with this, I present Nathaniel Hanson and his dissertation defense.
Thank you, Toshkin. So, all right. So with that wonderful introduction, I'm so excited to see a room full of people for my dissertation defense. I'm excited to share the work that I've done over the past 4 years with you all. So the dissertation is entitled Material-Informed Robotics, Spectral Perception for Object Identification Parameter Inference. So there's a lot of words in there. So over the course of the next 45-ish minutes, I hope to convince you I know a little bit about these topics and to convince you, hopefully, why you should care about these topics as well. So as my background, I did my bachelor's in computer engineering at the University of Notre Dame. I've completed my master's in computer science at Boston University, and I'm ecstatic and so proud to be a student here at Northeastern in the Institute for Experiential Robotics doing my PhD in computer engineering. So as an overview of the things that we are going to talk about today, we are going to look at, we're going to take you on a journey through my dissertation. So we're going to go over some background. We'll go over some of the terms and things that I think are relevant to our discussion. We'll talk about what other people have done in this same space, the shared research space. And then we'll go into 2 different research thrusts that have defined my PhD. So we'll talk about terrain sensing and terrain perception that are centered around the use of spectroscopy and hyperspectral imaging. And then we will take another detour through looking at sensing for in-hand manipulation. So looking how we can design spectral sensors and process spectral readings to be able to infer the material composition of items that are held in hand. And at the end, we'll sum up everything, add some final words and some opportunities for research, future research. So for background, I think it's always useful to bring everyone onto the same page so we can be sure that we're speaking the same language. So the research that is in this dissertation is, I can get rid of this. Let's see if I can get rid of that. Okay. So my research paradigm is focused squarely on this realm of what we call material-informed robotics. So it is the idea that we should have robots that can sense and act based off of what the material composition of the world is. So a lot of robotic research in the past has been structured around this idea of what we call semantic object recognition. So we want to tell that this is a cup. And that's our modus for operating the world, is recognizing objects by their function. But that's not the complete picture of how humans operate in the world. when humans are operating in the world, they have an understanding of what things are made out of. For instance, we know this cup is paper, and we know that it has a certain force at which it will deform. And so we have to change our grasping strategy appropriately. So from this research paradigm, we're interested in how do we design sensors and processing methods that enable us to act in the real world. And so, I just stopped sharing. Okay. So by this, we mean we want to understand by material, the elements and constituents that compose items in the real world. And at the same time, we want to understand this idea that research that we do ought to be grounded in the real world. So we should be using real sensory, experientially acquired data to be driving our research. So some motivation, we want to think about where is material present and why is that a pertinent research topic for robotics? So one of the first places that we can think of is where we see robots kind of present in our everyday life. And one of those areas is this realm of autonomous driving. So in autonomous driving, we look at surfaces. So surfaces are abstract in shape and dimension, and they have a material to them. So we have asphalt, we have snow, we have grass, and they have different surface friction coefficients. And each of those has a certain level of affordance of what we are able to safely do on top of that surface. And so, but it's also important to understand the nuances of how material can quickly change a robot's ability to traverse and navigate through an environment. So if we consider a road like this, which is normally would be very traversable, if we all of a sudden look a little bit closer, we can see that surface changes to black ice, at which point the surface becomes something that we would not want to traverse across. And so something that we have to be able to have sensors and methods that we can perceive and identify these on the fly, and in real time. And so if we go one step further to understand where we see material, if we go from a very structured road environment, we go off-road. So if we look at a road like this, or where there's really truly no road, we have a composition of a scene where we've got some grass, we've got some vegetation, we've got rocks, we've got some dirt that transitions to mud. And so as a roboticist, we ask ourselves, where is the safe path through this environment? Is it acceptable to go straight through the big mud pile? Or is that going to result in a scenario where the vehicle gets stuck and lost? Or is it better to take a more assured path over a surface which isn't heavily muddy? But we have to be able to understand and quantify the types of materials that we find in our surfaces for mobile robots. But material is not just something that's present in navigation for mobile robots. If we also consider a simple example that I brought up earlier of the cup, and like thinking about cup is made of material. So if we passed to a semantic segmentation algorithm, we just asked it to identify what is a cup. Like these would all be candid things that qualify as cups. They're objects which can hold liquid, but they're each fashioned from a different material, and the material that they are made out of has consequences. For instance, the glass cup is really firm, whereas the red Solo cup and the styrofoam cup are rigid and they'll buckle under force. So for a robot that needs to manipulate these surfaces, we have to ask questions such as how much force can we reliably apply to the surface, as well as will this object slip? So what's the friction? And what do I need to do to modify my grasp in order to have a stable contact force? But I know we've talked about material and object recognition from the perspective of let's look at inanimate objects. But for sort of our research paradigm, in order to get robots out of the lab and interacting with humans, they're going to have to come into close contact. And traditionally, robots have been quite terrible at recognizing the presence of humans. So this quite topical example from this past year of a computer demonstrating a newfound capability to play a game of chess against a human. And the human acted in a way that the robot wasn't expecting. So the robot expected to see a rigid chess piece. And the way that robots tend to grasp objects is they tend to apply as much force as possible to ensure their grasp is stable. The consequence of that is you end up with a broken finger. So we want to design sensors that can inform robots to understand what they're actually holding. So that all begs the question of how do we perceive material? So what are the ways that we can actually look at the world and understand what items are made out of? And so for this dissertation, the answer that we've come to use is a technique that's called spectroscopy and hyperspectral imaging. And so I know that term might be unfamiliar to people, so I'm going to give a brief overview on what this technique is and why we should care about it. So the best way to think about what spectroscopy is to use an analogy from human anatomy. So our eyes, we have a tricolor representation of color. So we see the world with red light, with blue light, and with green light. But it's important to understand that as humans, we can only see a very limited portion of the electromagnetic spectrum. So humans, we see about 400 nanometers of wavelength of light. But light is a continuous function that continues beyond what we're able to see. And the interesting thing that happens, especially as you move into the near infrared, is light that's reflected is no longer a function just of the color of the object, but as a function of the underlying chemical composition of the material. So essentially what we can do is by looking in these different wavelength regions, and measuring the amount of light that's reflected, we can essentially measure the material composition of items. And so for an ability to do non-contact material estimation in robotics is a pretty cool technique. And so what we do with spectroscopy is we evenly sample the electromagnetic spectrum, and that gives us an ability to estimate the material composition of items. So if we think about how humans see color as a tricolor value of RGB, there's an extension of this, which is what we call hyperspectral imaging. So instead of seeing just 3 colors, we can have images where we're seeing in many colors that extend out into the infrared. So instead of having 3 channels that make up an image, we can have hundreds. And by comparing the different reflectance signatures at points, so if we look at this example image here, we have reflectance curves for soil, water, and vegetation. By looking at how these curves value, we can do land cover classification. And this technique has been done by remote sensing scientists for decades. But it's never really been done in robotics. So in this dissertation, we're going to talk about how we can use this meaningfully to enhance robotic capabilities. Okay, so at this point, we'll transition to talk a little bit from background to more of what are people doing to pursue some of these questions of understanding surfaces, understanding materials, as well as building sensors. So some recent approaches in material recognition have really have also been focused on 2 different realms. Can we use multimodal sensing to understand the environment? So can we fuse information from visual as well as tactile? So when we interact with an object and understand the specific force feedback we receive. Other works have focused on using multiple different imaging modalities, such as polarization-based images, infrared images, and which are heavily computer vision driven techniques. But the real folly of those methods is they require millions upon millions of labeled samples that take hundreds of thousands of human hours to manually segment these items. And so that's a quite limiting factor, that these algorithms perform poorly generally on unseen environments, but then they also require extensive training and preparation to be able to work. But there's also been some other people who have been interested in how do we use spectroscopy, and spectroscopy has been shown to be useful from just a scanning stage to recognize the material composition of household items, to recognize broad meta classes such as foam versus wood versus metal. And so that's a promising springboard for us to jump off of. In terrain perception, similarly, there's been works that have been focused on how do we take multimodal sensing and also use it towards understanding. So as an example, you see a combination of proprioceptive and exteroceptive sensing from both audio and visual feedback. Some methods are focused on how do we minimize the amount of labels that are actually used in this process, and can we just, based off of what a human operator would do, can we learn to infer and have a label-less system? And then can we have methods which combine this? So can we have self-supervised semantic segmentation that builds upon both of labels and label-less methods? And finally, just as an overview of sensor fabrication, there's been some great works which have focused on how do we use light and optics to build soft sensors. So there's, starting in 2016, there was kind of this revolution of we can use optical waveguides, which are conduits which channel light. And by measuring intensity loss, we can infer curvature and contact. And since then, there's been some great advances in the field which have focused on optimizing sensor design, making highly transmissive grippers, as well as focusing on making selectively permeable membranes that can allow infrared transmission. So inspired by a lot of these innovations as we do in academia, we now present some of our own work. And so the first thrust of work that we're going to talk about today is this thrust into spectral sensing for terrain perception. So the first work that I'm going to talk about was originally presented at IROS in 2022. And so what this work contributes to the state of the art is we've built a mobile robot system which takes a multimodal sensor which is co-aligned with the contact patch near the wheel of a robot, and we collect spectral signatures as well as high-resolution macro terrain. We're looking at trying to understand how the local terrain under a robot can be used to infer and inform the robot of where it currently is in the world. And to do this, so it's a bit of sensor design as well as algorithmic development. So we develop a novel post-fusion model that leverages the strengths of individual modalities that we'll talk about. So the system that we built, so we're using a relatively small robot, and co-aligned with each of the wheels, we have this sensor array, which has a built-in halogen light source. It also has a fiber optic probe with a high numerical aperture, so it's got a large acceptance cone of about 60 degrees, so it's collimating light from a 0.5 centimeters off the ground. That light is channeled into the robot where we have a MEMS fiber optic switch, which changes which fiber we're reading from. And then we also have a high resolution self-focusing macro camera. So we're acquiring images constantly of the terrain as we're driving over it. And so we, at every point in time, we get a spectral reflectance profile from the contact as well as a macro image. And we take this system all over New England, so both indoors, outdoors, on the beach, over grass, and we collect a very large data set just to understand how terrain variability changes from both an imaging point as well as a spectral composition. And so to this end, we build out a large data set where we have some very nicely selected images. These are about as good as it gets for the image quality over 11 different classes. We have reflectance normalized spectral signatures, as well as we look at 1 second snippets of IMU data, and we extract motion features from them, such as acceleration, both linearly and angularly, as well as we take the second derivative of acceleration, and we get the linear jerk to try to understand how rough a surface is as a vehicle is driving over it. And that's inspired by some previous works which have been focused on using vibration-based characterization of terrain. So to model and try to understand and predict what sort of surface the robot is on, we use a fusion model. So we first take our initial data and we prepare it, and that yields our raw input signals, which we then feed forward into 3 different neural network models. So we use a modified version of ResNet, which is a convolutional neural network, which is pre-trained, and we train 2 additional final layers to it. So each of those models predicts an output, which is an unsoftmaxed probability for each of the individual classes. But instead of taking each of these probabilities and just post-multiplying them to yield and normalizing them as one would do, we actually take them, concatenate them into another feature vector, and learn a final post-fusion model. And what we find that's really great for is it can learn to account for uncertainties in individual sensors. So when one sensing modality is occluded, or especially when there's motion blurring in the camera and the data is essentially garbage, this is really good at handling those moments of uncertainty. And it places, when there's uncertainty in one sensor, it learns to place greater importance on another sensor. And so that gives us our final probability. And so our results from this fusion technique are quite excellent. But the main thing that I want to harp in on this slide is by using spectroscopy by itself is more accurate than using image-based classification, as well as the signatures that you're using are an order of magnitude less complex than the data that's used by high-resolution camera. So fusing the data together also yields higher accuracy. So with this work, robots are better enabled to understand what surface that they are locally on. Okay, So now that we can understand where robots currently are in the world and what their current state is, we want to look farther forward. So now we want to say, okay, if we can look directly below us, now what's the next 10 meters hold for us? And to do that, we've built out this system, which we call the hyperdrive system. And so it is a larger UGV robot that contains 2 co-aligned snapshot hyperspectral cameras. So those offer 33 spectral bands over 1100 nanometers of sensed wavelengths of light. And so we can acquire data from these cameras at a rate of about 50 hertz. So we can get near real-time performance. And we also have an inbuilt target, white reference target, which we use to dynamically calibrate these systems. So from this work, we released a fairly large data set. So it's actually the world's largest outdoor hyperspectral data set, as well as structured labels. And we define methods that we can use to calculate terrain properties, as well as to dynamically calibrate these systems so they can be operable in the field. Okay, so just a brief note on the hyperdrive data set. So like I said, it's the world's largest and most diverse hyperspectral vehicle-centric data set. So it's over 500 gigabytes worth of on-road and off-road images captured from Olin College. And it has co-aligned RGB visible to near-infrared data cubes, as well as shortwave infrared data cubes, as well as the methods that can be used to co-register all those images. We use labels that are from the Atlas ontology, so that's a data set that's put out by US Army DevCom, which they're trying to use as a standardized method to be able to compare semantic segmentation algorithms. And one of the things, I won't talk too much about the raw data from this experiment, other than we have some results that which show empirically that by using hyperspectral data, and looking at the reduced dimensionality projections of the data, we find there's a lot less noise in hyperspectral data compared to RGB data. And so if we look at all the different classes that exist, by using hyperspectral data, we find that there's better class separability. And we believe that in future works, that could be very beneficial to training semantic segmentation algorithms to be able to understand interclass differences. Okay, so there's a lot that's going on in this slide. So to motivate a little bit about what we're trying to do here, I want to talk about why we don't see hyperspectral cameras currently used in outdoor environments. And the real problem with hyperspectral cameras is not just a swap consideration, so like a cost or a size issue. One thing that we see that is continually a problem in these systems is these cameras need to be what's called reflectance calibrated. So the signal that a hyperspectral camera is able to obtain at any point in time is a function of the ambient illumination in the environment. And so as the illumination source changes, so as the sun rises and sets, as there's clouds that roll through the environment, as there's higher humidity, the light that's emanated from the sun is actually changed. And so in order to get good, consistent readings from these systems, we have to be able to calibrate the camera to operate in different and changing environments. And so what we're trying to show here is we took this system and we put it on the rooftop of Egan Hall for a couple days, just to look at what does the solar pattern look like over as there's weather, as there's clouds, as the sun rises and sets. And so what we can see in these plots, so these are correlation graphs. So we're looking at how does the spectral signature of the sun vary from one moment to the next. And so if there's this large cross feature, which is in these plots, and that's a function of there's very low signal. So this was when the system was out at night. But in the VNIR, so the VNIR, what we're seeing here is there's high correlation between subsequent readings. So as we can see from this little inset plot, so the readings that we receive from about 660 to 900 nanometers really only vary as an amplitude function. And that's great because that backs up what some prior work has shown, is that just changing the amplitude and amplitude correction is fine to calibrate systems in this domain. But as we look in the shortwave infrared, you see patterns of there's a lot darker colors, and that's correlated. That means signals are highly uncorrelated. And so from this sample plot that's pulled out from that red point, you can see that the readings here vary as a function, or the two signals that are elicited can't simply be multiplied, or there's no multiplicative constant which will make the signals equal to each other. So in order to overcome this pretty significant challenge, we collected a bunch of data, and our goal is to find a way that we can calibrate the cameras together. So towards this method, when we want to calibrate a camera for outdoor operation, we take we look at this one simple equation that we see time and time again in spectroscopy and hyperspectral imaging. So this is called reflectance normalization. And when we want to normalize the camera, we take the raw signal that we get in and we'll subtract off what we call the dark current. So the current that's caused by just ambient electrical noise. But we always want to normalize it against a reference signal. And the way that that's done is you will take a sheet of compressed Teflon, which is a white reference standard, you'll put it in front of the robot, and you'll basically use that of, given the current illumination conditions, this is the maximum signal that I can possibly expect to see. But for robotic operation and robot operating environments, that's actually quite a difficult consideration to manage. So what we want to do is, like I mentioned in the system architecture, we have a fiber optic probe, which is pointing to a very small white reference target on the vehicle. And so what we want to do is we want to generate, given this current reference target, so if we can measure the spectral signature with an onboard spectrometer, can we predict what this reference signal will look like for the rest of the vehicle and for the hyperspectral cameras? And so to do this, our problem that we're trying to solve is, given this input signal, so a spectrometer input S, and an output for a hyperspectral pixel I, we want to understand how those two signals map between one another, given the current device's sensitivities. And so we looked initially at this from an optics-based perspective, but there are so many intrinsics and unmodelable characteristics that are in the system that we found that this was a more complex system than we could find constants for it to generalize. And so we want to find an approximation of this function. And to do this, we have an input signal that's a vector 24, and we have an output signal that's a vector 24. And so what we build is we build an encoder-decoder style network where we use a custom loss function, which is inspired by spectral angle mapper, which is a type of similarity measure in hyperspectral imaging. And we can learn a function which is designed to do this dynamic calibration. So we can generate from a single point reading of a spectrometer, we can generate a white reference signal of a high resolution multispatial dimension camera. And so we showed that from our results, using a learning-based method, we can achieve superior performance in matching the spectral and minimizing the angle between these readings. And so some of the results from this calibration routine is, this is an image taken outdoors where we have a spectral on target as well as a calibrated color checker. And what we're trying to do here is, given this raw image, we want to minimize the distance between subsequent readings. So we want essentially to take the signals in the raw image, which are highly noisy, and we want to essentially clamp them so they're flat signals. And we can do that with our method. And as you can see from the plots of the reconstructed grayscale intensities, we end up with readings which are very nicely normalized. And so results are very good in the V-near. And then as we move into the shortwave infrared, we see similar performance in the shortwave infrared. We note that there is one anomalous band that we have at 1195 nanometers that's really caused by some high signal, very, very low signal noise. But our method is able to increase the contrast in each of these images, as well as make sure that our target of spectral on calibrated white reference remains uniformly bright. And from this calibration routine, we can start to ask some really interesting questions about our environment. So the first thing that we're interested in is, given these sensors have traditionally been heavily used for understanding vegetative health, that's a very traditional use for hyperspectral cameras, can we use these systems consistently in environments to try to understand where vegetation is as a prior to understand traversability? So previously, if I wanted to understand where there was vegetation in an image, I would need to use tens of thousands of labeled samples of what is a plant. But with this, what we can essentially do is we're modeling where there's chlorophyll absorption in the image. And by looking at that, we can understand as useful prior of where there might be vegetation. And generally for robots that want to stay on a path, that's a really useful way to simply bound where the robot may or should appropriately drive. And as we see with using and applying our calibration routine here, we yield much more consistent intensities for healthy vegetation, as well as when we apply a let's use method, which is used to provide a segmentation in a two-class assumption, we see that our calibration routine enables better segmentation of environments, especially environments that have shadows or heavily shadowed environments. The second question that we are interested in asking is, how can we understand where there's moisture in the environment? So if we go back to that very first image that I showed of where we have that muddy environment, we want to ask questions of not just is there dirt or is there mud, but how muddy is the environment? And so to do this, we built out this test bed on campus where we have soil and sand, and we measured the ground truth, all the soils, to understand with a relative humidity probe monitor to understand how wet that soil is. And we want to understand how do we map and associate ground truth readings from the relative humidity probe with the readings from hyperspectral camera. So we can see that the ground truth reflectance that we measure changes. We have a stronger absorption that develops at about 1300 nanometers. So we know that there's some good results here to understand how soil moisture exists. And now we want to understand how do we model that phenomenon. And so to do this, we formulate an optimization problem where we're trying to understand what is an optimized spectral index that we can use to essentially take two wavelengths of light and subtract their difference and then normalize against it. And we want to come up with a score that yields the maximum possible signal difference. And so we generate this optimization problem, and we find two wavelengths of light which are able to tell us how wet the soil is. And so we look at light at 1300 nanometers and 1119 nanometers. And by comparing those two wavelengths of light, and we can fit a regression model to this function. And so we can now look at images of soil and terrain, and we're able to tell, is this dry? Is this wet? And we can run this inference. This algorithm is extremely fast, including the reflectance calibration. We can run this at 100 frames per second over images. So we can dynamically pull these properties out and yield inference that's fast enough for vehicles to make decisions over them. Okay, I'm going to take a sip of coffee, and we're going to transition to talk about the second research thrust. Okay, so now that we've appropriately motivated that spectroscopy and hyperspectral imaging are useful in the context of outdoor robotics, now we're going to talk about how we can use them indoors to make a difference. And so the first piece of work that I'm going to talk about originally appeared at ICRA 2023. So this is what we call the slurp gripper. So this is spectroscopy of liquids using robot pre-touch sensing. And so from this work, we show that in-hand signals can be used to model spectral signatures can be used to understand what's inside of containers, including opaque containers. And we can do this from a form factor which is small enough to fit on a robot gripper. And these measures are repeatable and can be attained at a high accuracy over multiple different material types. So as similar to the vast imaging array that we use for outdoors, we build a specialized sensor that includes both a coupled fiber optic spectrometer as well as a fiber on chip, a spectrometer on chip, and a time of flight distance sensor, which we use to control a precise distance offset to the container in question, so we can make sure we obtain very reliable spectral readings. So the way that this gripper works is when we want to grasp an example, like this is a wonderful tub of oat milk, as one might have. If you first take light and from in the gripper, we put light incident onto the container. Some of that light will be incident on the container and will be reflected back. Some light will make it all the way through the container, and we have a Teflon tile on the backstop of the gripper, and that light will be reflected back into the sensor aperture. And then finally, some light will be incident into the container and will be scattered. And so the combination of all these sources of light yields a signal, which is a function of the reflectivity at each of the different wavelengths. And that's a pattern that we can look for over multiple different classes and understand, is this something that generalizes to different surfaces? And so to understand where this system works and to where it doesn't, we constructed a very large data set we looked in the fridge and pantries of all our homes and tried to find some good containers. And so we ended up with this lovely data set of both common containers that are both transparent, opaque, translucent, as well as common items. And we ended up with a wonderful permutation of data, which we then learned how to model. So we learn what we call a hierarchical model in this approach. So what we first do is we take input readings from both of the spectrometers. We reflectance normalize them. And then we do some manual feature extraction. So we take the first order gradient of the signal. And so we're essentially trying to manually extract features which are correlated with the intensities of the peaks and reflectance peaks and absorbance troughs. And we concatenate that into a single signal. We then learn two models in tandem. So we first learn a model which is learning to predict the container. So as light is shined through the container and there's reflectance and absorbance in that signal, we want to understand what is that contributing to the signal. So we learn to understand class probabilities that yield a container prediction. We then feed forward those results into a second model, which is learning contents. And so we are essentially learning a class conditional probability here. So we're learning to understand both the containers, but then also what are the contents given the predictions of the containers. So we know that the fact that liquids and solids exist in containers that attenuates light. And so we want to understand and account for the different intensities in those signals. And so this approach yields an accuracy of, we can recognize containers with 96% accuracy, as well as 85% overall for contents and 82% for both of them. Okay, so now that we've shown, so for the slurp gripper that we showed, that was what we call a rigid sensor. So it's made of materials that are very stiff, they don't bend, they're not, in any words, what we would call compliant. And so towards that goal of trying to make sensors that are soft and are forgiving, that won't break your finger if you get caught in them, we wanted to understand how do we make a gripper which is also soft and highly compliant, but can still maintain and generate highly accurate spectral readings. And so in this first piece of work, which originally appeared at RoboSoft 2022, we developed a soft finger, which has innervated fibers and an embedded illumination system, so we can generate signals, so we can take readings from in-hand objects. So we built the sensor, so we fabricated and etched a custom FR4 PCB, and we embedded lensed fiber optic cables. So these are miniature cables with a ball lens and a highly polished fiber cleave to increase reflectivity. So light can be collimated from the surface of the sensor pad and be channeled to a spectrometer, which can generate these material readings. And then we adhere the sensor pad to a hybrid manufactured soft gripper exoskeleton. And so from the results with a simple architecture, I won't spend too much on this slide, but I want to emphasize is we have good sensitivity at being able to understand and look at items in the visible wavelengths of light. But with this first design, we noticed that there was really strong absorption and noise that happened as we moved past as we moved past about 900 nanometers. So our ability to actually look in the infrared and try to understand material composition and some of those absorptions that occur in those wavelengths was severely diminished. So in order to do that, we knew that a second generation sensor was in mind and was in order. And so with that, we built this sensor, which we call SCANS. So this is actually a multi-function sensor. So we can understand and take readings of not only in-hand spectral readings, but it has a U-shaped waveguide, which we can also use to infer the conformal state of the gripper. So we can also measure the curvature. And so the sensor pad has no electronics. It has only light directing conduits inside of it. So it's a very flexible, very cheap to manufacture sensor, and we can pull out multiple readings about the state of robotic grasping with it. And so in order to understand how we should build a sensor, one of the things that we had to really consider is no one has really thought about how do we make optics in soft grippers in such a way that are conducive for manipulation and spectroscopy. So we spent a lot of time on material analysis and trying to understand optical transmission as well as absorption and how these materials essentially worked in order to have a high throughput optical sensor. So in order to actually measure light, we need to have a lot of photons that can be directed through the finger and into a spectrometer. And so one of the things that we discovered in our analysis of materials is we came across PMMA, which are a type of acrylic fibers, which have a fluorinated outer jacket coating. And so these have excellent light throughput. They're highly flexible, but they're not radially compressible. So their light isn't attenuated when there's contact made with the item, but they're still highly compliant and can bend along an axis. And so we selected this as a primary driving material to build out the sensor. And so, hold on. Okay. So the way this sensor works is, so we fabricate it very similarly to how we did the first generation. So it's fabricated with additive manufacturing and casting. So we use dragon skin, which is a platinum pure silicone based material as the base sensor pad. But then we also pigment it with titanium dioxide, which is a highly reflective white pigment that acts as a secondary cladding to help keep light within the sensor. And then we inlay fiber optics, these PMMA fibers within the finger. And so I'm going to talk a little bit about, there's 3 fibers in the finger, and we'll show a little bit about what each one of them does. So the first one is this U-shaped conduit. And so we put light into the fiber through an inbuilt miniature halogen source. And we read that out. And as the finger bends, the signal intensity decreases, which we can model and use to infer a curvature-based estimation of the gripper pad. We have a secondary fiber, which goes down the length of the pad and shines light to the end where it's reflected through a right angle prism. So light comes through this fiber and is reflected onto the surface. So we have an illumination patch locally in the contact pad of the area of the finger. There's another fiber which has a similar prism, which then has light reflected into it and back through the finger through a spectrometer, which we can then measure. And so through the system of using just in-hand optical fibers, we're able to measure the spectral reflectance profiles of objects that are held in hand, as well as curvature. And the goal is to, in the long term, use this curvature to be able to inform and provide some amplitude correction to the spectral signatures that we generate. So to understand just some performance of how this system works, we built out this benchmarking environment where we're looking at both the curvature from a ground truth perspective. So we have a motion capture system set up where we're measuring the radial curvature of the finger. So essentially what we're doing is, given these 3 points that are on the finger, we're fitting a circle to it and we're measuring what the central angle of the arc that the fingers occupy on that circle, as well as we're looking at the intensity loss that's caused as the finger bends. So as the finger bends and light exceeds the critical angle, light is lost out of the fibers, and is a repeatable phenomena that we can exploit to be able to infer curvature from a proprioceptive standpoint. So as a demonstration, we modeled both the curvature and the in-hand spectral signatures. So for talking about curvature, the one thing that I wanted to mention is that we have intensity loss that's uniformly 15% through the fibers as the finger bends. And there's a bit of hysteresis, which we think we can eliminate, but that there's a regular repeatable, there's a pattern of the linear model that we can use for every wavelength of light. There is a uniform model that shows that light is uniformly lost from the fiber. And the second time we looked at trying to look at the in-hand spectral signatures to understand where we have good detection range. And so from 400 nanometers up to 1100 nanometers, we have excellent spectral reflections profiles. We have a couple of limitations of the fibers themselves. So they have strong absorbances at about 1200 and 1400 nanometers, but we're still able to infer interesting material properties. So we can tell by looking at both qualitatively at this plot, as well as on the right, which is a spectral divergence map, we can look and tell the difference between lots of different types of plastics, as well as the different, looking at organic materials such as fresh fruit. So we can tell the difference between plastics, fruit, but we can also tell the difference between human skin yields a distinct reflectance profile. I think also just an interesting kind of side takeaway that shakes out of this is by looking at the optical profiles that's generated by the finger, this works really well as a proximity sensor. So we can tell when there is an object that's approaching the sensor, but is not actually making contact with it. So we can start to make inferences even when there's not direct sensor contact. Okay, So that is the scope of work that was done in the PhD. And now at this point, we'll transition to offer some insights into what are some future research directions. So continuing on our discussion of using spectroscopy and hyperspectral imaging in terrain mapping and analysis, where we want to go with this is trying to build out cost maps and to try to understand how do we use spectroscopy at multiple stages to yield insights into how we understand terrains. So with the first work, we showed how we can look at immediate costs so we can understand directly what's beneath us. We've shown with hyperspectral imaging, looking over a scale of meters, we can see what's in front of us. But there's a whole host of other sensors that exist at both an aerial level, from both aerial collections and satellite levels, that are collecting airborne and spaceborne multispectral readings, but they're obviously done at a much lower resolution than we're able to obtain using our sensors that are operating on the ground. So we've shown that spectral data can be useful in different resolutions and in different forms, but there's still unanswered questions about how do we pull all of it together? So how do we build systems that can use aerial hyperspectral data to build out sort of rough cost maps for the environment and help with pre-planning? And then as a robot is operating and acquires higher resolution data in the field, how can we use that measurements to inform and correct some of those initial understandings that we had from a larger, lower resolution map? For the work that we did on liquids, one of the areas that we're interested in is understanding how we can build sensors which are able to better manipulate containers. So we focused a lot, my PhD is focused very heavily on sensing and perception, and how do we understand the limits of basically what spectroscopy can do and what it can mean for robotics. But now it's time to answer questions of how do we use this in terms of control and to do action selection. So we've shown spectroscopy is useful at identifying liquids, but we also think that understanding the haptic profiles of how liquids shake and vibrate inside of containers is useful. So towards that end, we've been working on a next generation sensor set up for a gripper that has both a spectral probe to take readings, as well as using a gel site based tactile sensor, so we can understand how containers move and vary in hand as they're manipulated, both in terms of trying to understand the class as well as trying to understand how they react to actions. And the final area of research is going even further with the scans work. So we've shown that we can make a single point acquisition with the sensor pad, but by minimizing some of the optical components, we think we can put multiple of these sensor pads in a single finger. And that's useful so we can look not only at a single point of contact, but multiple points. And so kind of the idea, or motivating example that I have for this is we want to pick up fruit. So like lots of soft grippers are used in food processing. So could we pick up an apple like this, for example, and where we see under visible light, it looks perfectly unbruised, but as we start to look into the near and shortwave infrared light, bruise patterns become readily available. So can you do in situ classification and grading of objects while you're grasping them? And then second piece of that is while we're grasping items, how can we understand and
just in time.
Sorry, the window's open. We want to understand how we can model and understand curvature and what effect that has on spectral signatures. So can we understand the curvature-induced loss that comes from the waveguide and use that to correct the amplitude of knowing that that loss is uniform, use that to correct the signal that's coming from the in-hand spectral signatures. And so I return to, at the end of all this, my favorite cartoon, which comes from Adelson and his seminal paper on material perception called Unseen Stuff. And so if we want to think about what the current state of the art is in robotics right now, robots are really focused on this idea of recognizing rigid objects that have very defined geometric properties. So robots are really great at that whole idea of recognizing it's a spoon. And that's fine. Robots, there's a lot of great work that's been done toward that goal. But in order to have robots that can really, truly be pervasive and work with a whole variety of materials, especially objects which have no defined geometric properties that are very abstract, they need to be able to understand material. They need to be able to understand what's ice cream.
You don't want the robot eating your ice cream, do you?
Maybe that's the end goal. But I think at the end of the day, we want to have robots have a more nuanced understanding of what the world is made out of. And to do that, hopefully we've motivated that we need a little bit better or a little bit of a rethink of how we're doing perception. And there's great abilities that can be gained by thinking about the world in a slightly different light. Okay, so at the end of this, I'm so happy to thank all the people that are here. One, for showing up for my dissertation defense. Thank you for getting up at 9:30 on a Friday morning to come in and enjoy some free coffee and bagels. But then also, I'm so happy for all of the professors, all of the postdocs, the research scientists, everyone who gave of their time and effort to help make me into the researcher that I am today. Thank you to especially the River Lab and the Parsons Lab for all the grad students who really put time and effort into making me a better scientist and engineer. To my committee, thank you all so much for putting up with my questions, for entertaining my ideas. Thank you for giving up your time and helping to make another academic. To all the folks at MIT Lincoln Laboratory who were some of the most supportive folks throughout this entire journey, thank you for being here. Thank you for encouraging me and inspiring me to want to shoot for higher academic goals. And I want to especially shout out all of my undergrads. There's a number of undergrads here who I've worked with over the years. Thank you for being my guinea pigs and learning how to mentor people and how to lead research programs. You have taught me so much more beyond just helping lighten my load with research. Thank you for letting me try my hand at being a mentor. It means like a lot to actually have worked with all of you. And then finally, I'm so grateful for all the family and friends who have been a part of this entire journey. Thank you for getting me out of lab and encouraging me to go see things that aren't my computer screen at 2 a.m. Thank you for being my support network throughout the roller coaster that is a PhD journey. And so this is my work cited for everything I've published as part of the PhD. And with that, I am happy to take any questions that you might have. So I know there was a question. There's online. So does it make a difference if liquid is water or some other compound fuel? Yeah, so it's a good question. So as part of that data set of liquids that we collected, we looked at what we would call fluids. So both traditional liquids as well as granular solids. And so we showed that we can have recognition not only of like water-based compounds, but we can also look at non-aqueous based solutions, and that works fairly well.
Questions from the audience?
Did you explore like exotic materials, like say for example, Manta Black?
So that's always a great question of like, so the long and short is if you want to trick like spectroscopy, like if you want to pick really like exotic materials, like sometimes that's a difficult constraint. We didn't consider Manta Black. We tried to make this research focused on sort of common items that you might find in your house, and I don't know, maybe you have some Manta Black lying around. I personally don't. But I think
like glass flooring or like falsifying like free. So it's like this, you would trip the spectroscopy.
Yeah, so that's actually like so to that like end, like we have, it's not in here, but I have some data from like where sometimes like you'll see like a metallic surface where it's like metallic painted plastic, and like we can recognize that. But there are limitations to where spectroscopy will work. So, like spectroscopy is not the right tool to tell the difference between different types of metals, for instance. We can generally recognize that something is metal, but not that it's like one type of metal or another. And so that's really a point where you can look at different types of hyperspectral imaging. So if you look in thermal infrared, there's some ability to distinguish metals there, or just other types of sensors. So spectroscopy is great as a non-contact material estimation technique, but there's like humans aren't unimodal sensors. We look at the world, but then when we have uncertainties, we go and mess with objects to try to understand what they are. That's kind of to those more confusing type of objects. That's kind of a paradigm that we also expect.
Thank you. Great work, man.
Next question.
Oh.
Yeah, a lot of the work that you talked about focused on spectroscopy and like supervised learning techniques. Can you speak a little bit about unsupervised learning and spectroscopy?
Yeah, so there's a piece of work that we have where we actually, I guess, not in this dissertation, but I'm happy to pass along, where we look at just looking at spectral signature composition and trying to look at anomalous items. To like find and identify anomalous spectral characteristics and use that to identify, like in a scene where there's no prior knowledge, what doesn't belong. There's also a lot of work that we can do in terms of like looking and building out codexes. That's a really that's a great avenue for future work of trying to build out sort of known libraries of materials. And I think that goes to our understanding of one of the directions for future work that we showed of using like shaking items and trying to understand how they like plastically will deform as we manipulate them. It would be great to have sort of learning in the wild and sort of build out an embedding of as like what the spectral characteristic of those items are, but also like force deformations. So you can try to build out, and even though if it's something you might not know, can you compare it to items that you do know and try to understand and place some sort of distance, similarity or dissimilarity between them.
For the scans finger gripper work you did you look at any work with multiple of those sensors interacting on one time with each other, or was it always just a single?
So at this point, we've only done a single one just because of for time and material constraints. We've only been able to make single standalone fingers. But that's actually an interesting question of how does the light from one, especially if you have them in like a grip where they're perfectly like parallelly aligned, like do they interfere with each other? Yeah, that's a good question. I would say we can probably the results that we had on the slide showed that we can very much recognize when the finger is in self contact with itself, and I assume that the signal for when it's just looking at another sensor that's some distance away from it would be relatively similar, just probably at a lower intensity, just because there's light that's lost over that transmission distance. And I'm sure we could also probably learn to recognize what's the raw signal of the light. I think that could definitely be done.
We got a couple questions. At this couple.
Are there manager calibration cards you could keep in camera view at all times to improve spectral corrections? So that's actually what the prior state of the art has focused on, is either having the robot drive, like do some operations and then drive around and always come back to a calibration target. The drawback of a method like that is if you have a robot that needs to go from point A to point B, and you're driving through heavily shadowed environments where there's weather rolling through, you need to be able to dynamically calibrate the system. You can't continually return to a target. For some places where you're doing agricultural robotics and like you can always come back to a shed or something every so often, every couple of minutes, like that is an acceptable consideration. But for sort of those work is funded by the Army, and they're very interested in sort of the long-term mobility questions where you don't always have a set operating base. Could we integrate ultrasound spectroscopy or some part of that used here? So we're using reflectance-based spectroscopy in this work. There's a whole host of other techniques. So there's Raman-based spectroscopy, there's Fourier transform spectroscopy. So spectroscopy is just it's a very big bubble in terms of what we mean. So by actually saying spectroscopy, we're very limited in the scope of what we're using. And we're trying to use sensors that are of the right swap for use within robotics. So as you start to move in some of these more exotic based spectroscopic techniques, your cost gets exponentially higher as well as your resource constraints. So we wanted things that could be reasonably used on a robot in the current fabrication techniques. I think that's all. Yeah, so that's a
Can
good.
can you read the question?
Sure. So the question is the curvature focused light inside the U-shaped path inside scans shielded protected from other light paths that are detecting object materials? If not, doing so may give you better curvature data, vice versa. Okay, so that's an interesting observation. So as you noticed from, I can just go back to that this figure of so I think what he's trying to allude to is there's light bleed that occurs from the sensors. And that's generally what that's associated with is light is just generally lost as it's coupled into the fibers. So light can be lost in that way, but it's not, that light is lost as it's introduced from the illumination source at the base of the finger. It's much less likely that light will be coupled into the finger sort of from just the ambient environment that's not from these ends. So the ends of the fiber are fully encapsulated in this onyx fabricated gripper pad. So stray light isn't really introduced. And the odds that light is actually going to be bent into the fiber through through both the secondary cladding and the fluorinated jacket is fairly low.
So Nathaniel, one of the cool things you've been doing with all this stuff is really binary detection. This container and this liquid or something like that.
Mhm.
What are your thoughts on trying to quantify, say, purity of a liquid, right? So let's take milk,
Mhm.
right? Whether it's 2% or whole or skim. Do you have enough SNR coming in that you could do that, or what would you do for something like that?
Yeah, so for that specific question, especially for milk, like trying to identify different types of milk. So we looked at for the slurp work, we looked at whole milk versus oat milk, for instance. In order to really sense like lipid concentrations, which is what you want to infer to be able to tell like if is it full fat milk versus skim milk versus oat milk, you want to be looking at about 1700 nanometers and a little bit further. That's where some of more of the liquids like manifest. And so that's been done to like, I've read way too many actually milk quality journals as part of this PhD.
Right.
So it can be done. I would say that would require some investigation as we go further out. So like as you see for this sensor here, it goes out to about 1600, just past 1600 nanometers. So you'd probably need about another 200 nanometers.
Okay, so that's almost too specific an example. Can I give you one more example?
Sure.
Let's look at something like I was going to say acid, but let's say vinegar.
Yes.
And vinegar concentrations where you have a continuous curve.
Mhm.
And and what are your thoughts on that? Again, this is not for you, this is for your next generation of students. Okay, what would be the next steps to take this binary classification of multiple stuff and try and now say we can do quantitative comparisons of concentration or some other measures in there?
Yeah, so to answer that question, like that's a good I think one of the struggles of robotics PhD is trying to answer interesting spectroscopy questions for like applications versus like what is the pure robotics like science. But I think one of the way that I can answer that question is if we going back a couple of slides to, I'm just gonna mash this button. So if we look at like how we did this, so there's two ways that you could approach that question. We could treat everything as a black box and just throw deep learning at it. But I think the real value of what spectroscopy yields is you can, with just a little bit of analysis of what are the optimal pairings, is you can start to look at the wavelengths of light specifically. And so kind of like what we did for moisture detection, where we're looking at specific pairings, the bands that yield the maximum signal difference, you could do something by having some curated samples of like, if you're trying to look at like vinegar, like in concentration, you can look at which wavelengths of light yield a maximally significant difference, and you could build an index for that. And there could be ways in the future to like have that done as an autonomous process, where like you give it the framework, but the system and collecting samples learns how to build out what's the right index.
You had a question? Yeah.
Yes. So rather than attempting to classify what kind of material an object is made of, did you do any work, or is there avenue for work in simply trying to recognize qualities of an unfamiliar material? So say you have a robot who needs to manipulate something, they, rather than trying to conclude what exactly it is, just say, I'm not sure what it is, but it looks like it's slippery, it looks like it's rigid, that kind of thing.
Yeah, so that's definitely something that we've thought about, and we've kind of I've given some thought about how we would like build up that, and that's I think what we from the data that we're collecting for that liquid manipulation work, so like shaking containers, looking at spectral signatures, like, and this actually builds off of Vedant's question earlier. How do you learn from basically like how do you bootstrap a knowledge set, and sort of like look at properties, but then also learn to associate properties, which is, it can sometimes be an interesting thing because then you end up with human sort of intuitive labels for how you might classify different items. Might not be squared with how a machine learns to separate, like what's the difference like between, I don't know, like toothpaste and yogurt might like semantically be very similar to a robot in terms of like viscosity and behavior. So that is a good question. We think by looking at dissimilarity in especially for deformable items, looking at how they like deform under force and measuring that, as well as like looking at where there's distinct, we know pretty well. I didn't go too deep to avoid boring people with like overly looking at like the chemical spectrum, like what specific material compositions trigger absorbances, but we can look and see like based off of those signals where there's distinct material items in the spectra.
Great thought.
Thank you.
So the whole idea is around material aware robotics.
Yeah.
Why does that matter? I personally go around my life looking at things and interacting with them without much thinking about the material. So I look at this cup. Maybe if I'm environmentally conscious, I'm thinking, okay, great, it's not plastic, but I'm basically looking at the fact that I can pick it up and use it. How does your work feed into the robot's actual planning and action taking? Do you see material directly linking with what the robot does, or do you think there's an intermediate stage?
So yeah, so like our work is focused on the perception of materials, but I would also argue that then there's some great, like this also pulls into like the psychology of perception, that humans implicitly understand material. So like even though you are not categorically like thinking about like same way as like, oh look, that's a cup, like you were implicitly like recognizing that it's made of paper, and your actions and affordances of how you interact with that item do change. But it's something that humans are so innately good at that we don't have to think about it. But as I'm sure you've seen from like robots, you have to be very explicit about how where you interact with items. And so I do think there's like this work in one sense, yes, you're right. Like it's intermediary in the step of now we have robust perception that we can start to marry towards for those object recognition models. So to go back to the example of the cup, you like, yes, you can recognize it's cup, you understand sort of what like, and you can do sort of, if we can think about in a task planning perspective, like, you know, your end state and your goal state, but then as along the lines, if we also think about material, I'd argue you think about it even more explicitly when you're like carrying a cup of liquid and your goal is to avoid spilling it. So there's means to understand how to manipulate material that really are good prior knowledge. So you know that at no point you can exceed some force rating on how hard you are gripping a cup to avoid slipping it, crushing it. At the same time, like when you're moving a liquid, especially in like an open cup like this, you want to make sure that you're not sloshing it, because once you start to slosh, it becomes really an unrecoverable behavior.
So do you, just to clarify then, do you feel that the material awareness in between, say, any robot action taking, there'll be some kind of affordability reasoning, which
Yes.
would take as input?
Yeah, I think that's the real sort of next hurdle is how do we build from the like the perception, which was a challenge in of itself, how do you build that into affordability and then optimal action selection?
All right, one last question from the public.
Drake here.
What improvement percentage do you generally see compared to like just RGB methods?
Yeah, so we have, so there is one piece of work that we have. So the very first thing that I ever wrote was we were just looking at a very, despite how much this work keeps coming up, a very dumb piece of work where we're looking at images of real fruit versus fake fruit. And just a very simple exercise of, can we like distinguish between materials, especially in like visually tricky scenarios? And the answer is with using image-based data, and like we have like 10,000 labeled images of fruit, which are still on my iPhone for some reason. You can, even with like a state-of-the-art convolutional neural network, you can only get like 66% performance, so slightly better than a coin flip. But with spectroscopy, we could get up to 90% performance. So using lower dimensional signals, you can still, you'll see significant performance improvements. I don't have metrics on like looking at the outdoor data sets and like with a fully trained semantic segmentation network, but our analysis of looking at reduced dimensionality projections shows that there's better intra-class separability, and we think that can be useful.
Yeah, if I recall it, the outdoor one, like the first project you showed was like 4% improvement, right?
Yeah, so so from that one, that was so those were very high resolution images. So it was about 4% for that data set, and it really does depend on the application. And like, so the surfaces were distinct enough compared to like, if we look at the visually tricky example, like of the fruits where they're all similarly structured, similarly colored. The surface trains also had marked textural differences. So like grass looks very distinct from brick, from ice. So there was also spatial features that a neural network can use in those works to extract some meaning.
One last question. Have you thought about, have you thought about, this is playing off of what Mark was asking a minute ago, thinking about trying to detect objects that are hidden. So I'm thinking demining, I'm thinking landmines, I'm thinking IEDs.
So it's funny that you mentioned that. So we have from the Olin College data set collection, I had another wonderful undergraduate student who's actually online right now. And so some of the data that we collected there was we took large just steel segments and like buried them in the ground and had them partially exposed. And so what we're interested to do at some point in the future, I've not quite gone around to it, is looking at that data and trying to see from like a scene which has a natural composition generally, so between like gravel and rocks and vegetation and wooded stems, can we start to pull out anomalous features? And there's a lot of work that's been done in like the remote sensing community to look at target identification from spectral signatures, but we also think for at least things that are partially exposed on the surface, like we could probably pull out metal.
All right, we're going to take Nathaniel. All of you will get comfortable that it's all